AP Calculus students, how you doing today? Welcome to example video for 3.3b, the first derivative test, incredibly important. We're going to do some more examples here, number 8, 28, and 40, just because each of them has something a little different, something outside of the basics from 3.3a. So notice I already have my first derivative chart set up here. I haven't made the columns yet because now we kind of can see that that it's possible for you to have different number of intervals, anywhere from 1 interval to even up to 5 intervals. So we'll make the intervals as we go. So now we see abbreviations. This is our intervals across the entire domain of the function that we have been given, either from negative infinity to infinity, or if it's a square root, only positive, or if a domain has been given to us. And these intervals are broken up by any discontinuities or any critical points. Again, students will tend to remember their critical points and forget to check for discontinuities first. A lot of times when you find the critical, when you take the derivative, all of a sudden those discontinuities will show up anyway, but I like to check them ahead of time. We'll pick test values within our intervals. Then we'll test those values in the derivative to see if it's positive or negative. And then from there, we can easily say if the function's increasing or decreasing, and we can find any max or mins. So let's go ahead. This is number 8. You were given y equals x squared over 2x minus 1. Now, because this is a polynomial in the numerator and denominator, this is a rational expression, and it is continuous everywhere from negative infinity to infinity, except for where the denominator is 0, right? Notice that that would happen at 1/2, right? So I do have a discontinuity at x equals 1/2. So I am going to hang on to that though. I tend to circle any values I find that are going to break up my interval because I may find some more critical points on either side of 1/2 when I do the derivative. So let's go ahead and take the derivative. The derivative would be, I'm going to use the quotient rule here, the derivative of the numerator times the denominator minus, I'm going to keep my numerator and multiply it by the derivative of the denominator. If you don't mind, I'm just going to put that 2 right in front, all over the denominator squared. Now for critical points here then, right, here's my CP, undefined or equal to 0. There we go. Now if I asked you where this derivative, we might want to clean it up a little bit, is undefined though, you would all of a sudden be reminded, oh my goodness, there's a problem with the 1/2 here. So what do I write here? I'm not really going to put x equals 1/2. I could, I already found that discontinuity. I took x equals 1/2 out of the domain, and I'm just going to put DOD, defined on domain. And the domain is, excuse me, the domain is all x's except x equals 1/2. Again, if you hadn't discovered this and you said that it was undefined at x equals 1/2, in the end, you would still be okay, right? Now, where is this equal to 0? That would be where the numerator equals 0. So let's work this out a little bit. This would be a 4x squared right here. We can do a little bit better than that. 4x squared minus 2x squared is 2x squared. And then minus 2x here. And we can find where that equals 0. When I factor this, I'll factor a 2x and I get x minus 1 equals 0. Right? So that happens at x equals 0 and x equals 1. There we go. I circle those so I don't lose them in the process. And now I'm ready to break up my intervals, right? So my intervals go, my lowest x would be negative infinity. And I first get stopped by a 0. I will start at 0. And I will get stopped by the discontinuity at 1/2. I will start at 1/2 and I get stopped by the critical point at 1. And last, I will go from 1 to infinity. So in this case, we have 4 different intervals, as you can see here. Let's pick test values. How about a -1 here? How about a 1/4? How about a 3/4? And how about a 2? Right, trying to keep it as easy as possible. Let's test that derivative. Now, notice that I think I'll write the numerator a little bit better than I had it, right? For the derivative, we agreed that that was 2x times x minus 1 over 2x squared, 2x minus 1 squared. Okay, let's take a look here. Again, when I cleaned up this numerator, I ended up with this expression, and then I factored it to this expression. So either one of these is perfectly fine to have in the numerator, but I think the factored form is nicer. Now, when we're trying to decide if this derivative is positive or negative, right, we don't really care what the actual output is as far as the value. When I put in a -1, I don't care what the actual output is. I just care if it's negative or positive. Same for a 1/4, same for a 3/4, same for a 2. So this actually isn't as hard as you think, because take a look at the denominator here. The denominator is always positive. So we don't have to look at the denominator at all. When we're putting in our test values, we only need to look at the numerator. So take a look here. When you put a -1 into the numerator here in here, notice you will have a -1 here, a -1 here will be a negative times a negative, which is a positive, right? That's all I care about. Let's put in a 1/4. A 1/4 here will be positive, here will be negative. A positive times a negative is a negative, right? No need to overthink this with the fractions. Let's put in 3/4. When I put in 3/4, again, positive, negative, and I get a negative. When I put a 2 in, I get a positive and a positive, which is a positive. Okay, it's easy for us to say then increasing, decreasing, decreasing, and increasing. Excellent. Now let's go ahead and let's do our max and our mins. All right, let's check here, here, and here. Now, here we have it, the function is increasing and then decreasing. That would be a maximum. And that would be at the point 0, and we will get the y that goes with that. You could do it now. I tend to wait until I go across. Notice that it's decreasing and decreasing, plus there can't be any max or min. There's no point at 1/2. This was in fact a discontinuity. There cannot be a max or min there. So we're just gonna put none. Here at 1, the function was increasing, then decreasing. That indicates a minimum. And that was at 1 comma, there we go. Now I actually think on number 8, all they asked was for the increasing and decreasing intervals, but hey, we might as well do the whole thing, max and mins, right? When you go back to the original function, when you put a 0 in, you get a 0 out. And when you put a 1 in, you get a 1 out. There we go. There's the maximum, relative max, relative minimum. Okay, now I know that may seem strange. You're like, oh, but look at that. That number is less than that y value is less than that one. And it's if you graphed this picture, right? In fact, they do give you a picture, right? And they do show, right, there is a maximum at 0, 0. That's relative in its interval, its surrounding interval. And then there also is the minimum at 1, 1. Again, that is in its surrounding interval. And you can see the picture right in the book, right? So we don't even have to look at that. Okay, so that was number 8, right? Bit going on there. We had a discontinuity. Okay, let's go ahead and erase then. And let's get ready for number 28. And let's see why why I chose number 28, just making sure it's still recording. There we go. Okay, let's stretch this out a little bit. There we go. Okay, on number 28, they are asking for everything, increasing, decreasing, relative max or mins. I just realized after I erased number 8 that I should have given a nice list at the bottom. I did give a list of the maximum and minimums, but I also should have given a list of increasing and decreasing intervals, right? I should have read it from my chart, right? Because those AP readers will not do that for us, okay? I got distracted by the picture in the book. So we will be sure to do that this time. Okay, they're asking for everything. Okay, and we don't want to shortcut it. Number 28. Okay, let's see why I chose this one. F of X, we can see why automatically, because the function is not a polynomial or a trig that we're used to. It has a rational exponent, right? And usually in a polynomial, these exponents are integers. Okay, so let's take a look here. First of all, any discontinuities? No, I can put any value I want in for X and produce an output. So the domain is from negative infinity to infinity. If you're unsure with that rational exponent, you can graph it and take a look. Or notice any X I pick, right? If I pick X to be a positive value, right, then I can take the cube root of it and square it. If I have X as a negative value, I can take the square root of the cube root of a negative value and square it. So, and same with 0. So any X is fine. So all the X's are in the domain. Okay, let's find the critical points. The derivative would be, I will bring the 2/3 out front and multiply it and reduce the exponent by 1. That would be X to the negative 1/3. I'm going to write it as a cube root or an X to the 1/2 in the denominator, and then I get a 0 here. Let's do those critical points. Undefined. And where is this equal to 0? Okay, let's take a look here. So first of all, this derivative is undefined at X equals 0, right? A 0 here would make the denominator 0. So we do have a place, I'm going to circle that, that's going to break up our intervals. We do have a place where this derivative is undefined. Notice that that doesn't always happen, okay? Where is this derivative equal to 0? Nowhere, right? The derivative, this is a fraction. What would make this fraction 0 is when the numerator is 0 and it's a 2. So this is nowhere. All right. So let's go ahead and write our intervals. This time we only have 2. We're going from negative infinity to 0. And from 0 to infinity. All right, test values, how about negative 1 and 1? Okay, and let's take a look. Notice again for the derivative that the numerator is only positive, so we only have to look at the denominator. If we put a negative 1 in, the cube root of that is negative and the denominator is, and the numerator is always positive, so we get a negative. If I put a 1 in, notice the expression is positive. So we do have decreasing and increasing. There we go. Relative max or mins, we have decreasing on the left, increasing on the right. That is a minimum at 0. And to get that y value, let's go back to the original function. 0 to the 2/3 is 0. Minus 4 is negative 4. There we go. So in conclusion, this time we're going to write it, right? We found that there are decreasing intervals from negative infinity to 0, increasing intervals from 0 to infinity, and we found our minimum right there. Okay, last one, let's try number 40. Okay, on number 40, it's a piecewise function. And please remember, and you may have noticed, that piecewise functions are not the exception, they are the rule. We keep coming across these, right? So don't let it throw you. Just find your, go, no, I'm not gonna let this mess with me. What are my steps? Now they're asking the same question as the last problem. They want increasing and decreasing in max and mins. Okay, so let's see. On number 40, they have f of x equals 2x plus 1. And that is for x greater than, or less than or equal to -1. And they have x squared minus 2 for x greater than -1. Okay, I'm just going to step back, make sure that I wrote it okay. Let's see. 2x plus 1, x less than, good, x squared minus 2 for x greater than -1. And really, when you think about it, if you needed to, you could graph this, right? This line 2x plus 1 and that parabola x squared minus 2. Without a doubt, you could graph this to help yourself out, see where it's increasing or decreasing max or mins. But we're just going to go ahead and do the algebra. So let's take a look, first of all, any discontinuities. First of all, 2x plus 1 does not have any discontinuities on its own, and neither does this parabola. Let's see if it's continuous, if this function is continuous. We're at -1, right? So when I put a -1 into this function, I'm afraid I'm going to, no, I guess you can see that. When I put a -1 into this function, I get a -1 out. When I put a -1 into this function, I get a 1 minus 2, a -1. So I checked, there was a possibility for a discontinuity where they connect these two pieces. And it turns out that there's no discontinuity. So I checked, right? Okay, now, next then, let's check for critical points, right? So let's just put no discontinuities here, reminding ourselves that we checked. Let's take the derivative. That would be 2, would be the derivative of the line for x less than or equal to -1. And 2x would be the derivative for x greater than -1. All right, let's take a look. I think I'll go off to the side here. I think there's still room. CP undefined. And where is this equal to 0? Okay, let's take a look. So first of all, this derivative 2 is always defined, right? And this derivative on its own 2x is defined for any x. So the only place where the derivative might not exist or might be undefined is where they meet at -1. Notice when you put a -1 into this derivative, you get a 2 out. When you put a -1 into this derivative, you get a -2. In other words, the derivative is not the same from the left and the right of x equals -1. One derivative is 2 and one is -2. So we have the derivative is undefined at x equals -1. Let's circle that. That'll go in our interval. Where is the derivative 0? Well, let's see. The derivative is 0, never here. It's always 2. Here, 2x, where is this derivative equal to 0? No, notice that happens at x equals 0. So we did find a place where the derivative is undefined, and we did find a place where the derivative is 0, and those are 2 critical points. So let's go ahead, our intervals then, right? We're going to start at -infinity. There was no discontinuities. -infinity to infinity. -infinity, our first stop interval break is at -1. Then from -1, we get stopped at 0. And then from 0 to infinity. Test values, how about -2? How about a -1/2? And how about a 1 here? Okay, let's check that derivative. Okay, now when x is a -2, right, this is the derivative that is happening, right? This is the derivative for x less than or equal to -1, right? And -2 is less than -1, so the derivative is positive. It's always a 2. When we're at x equals -1/2, notice -1/2 is not less than or equal to -1. -1/2 is greater than -1, right? And so this is the derivative that's happening at x equals -1. And we get -1/2 and we get a negative out for the derivative. There we go. At 0, sorry, I'm looking from 0 to infinity. Our test value is 1. Notice this is the function that's going on, and we have a positive here. So notice we have increasing, decreasing, and increasing. Let's see if we can find any max or mins. There we go. Where at -1, we found that it was increasing on the left, decreasing on the right. That's a maximum. And what is that point? At -1, we'll find the y value that goes with that in a moment. Where x is 0, right? Decreasing, then increasing, that's a minimum. And that's at 0. And let's find where that's happening. So we need to go to the original function to get these max and min points. Where x is a -1, this is the function that's happening, right? So that would be a -1. I think we had already worked on that, right? A minimum, when the x is 0, this is the function that's happening, and we would get a -2. So in total, our conclusions are, here's our max, here's our min. Our function is increasing from -infinity to -1 and from 0 to infinity. And the function is decreasing on -1 to 0. There we go. So notice again, no matter what you've been presented with, just go and go, nope, I know what to do with this. I know what my steps are. I know it looks weird. I can still do this. And I hope you have a great day. Thank you.